Good afternoon, everyone. So before I begin the presentation, I want to appreciate Justin Tai, our first speaker, for lending me his template of presentation. As you might notice, we use the same one. So my topic will be building the globally accessible PRISMS small radio telescope. And I'm thrilled to share the journey. I'm a high school student from Princeton International School of Mathematics and Science, also known as PRISMS, and that's the place we build the telescope. I'm going to break down my presentation into 6 topics. First, my inspiration, as the professor mentioned, our passion of the research, and how we conducted observation, my remote website control functionality, and how we track celestial objects such as sun, and how I made signal analysis, also future research. So I started this project for my community. One day my engineering teacher, Mr. Kam, came to me. He asked me, I have an old L-band satellite dish. Do you want to change it to a radio telescope? I said sure, because when I was in CCIR data-driven astronomy course, when I'm facing so many astronomy data, I actually wondered how we measure the data. So that is why I started this project. PRISMS is a STEM-heavy high school. We have very good laboratories, but we have limited astronomy access. So I started this project for the community. Here, when I started, I was totally new in this area. So I started with buying a constructed system to learn about it. So I bought this antenna here, which is the small TV dish, and an LNBF, a bandpass block with a feed horn, which is this little part, and an LNA low noise amplifier, I don't think it's in this graph, and an SDR dongle, and my laptop. So what it does is it receives signal from the universe, and then it go all the way through, it amplifies it, and change it into computer readable signal. And the computer will analyze the data. So this is the software we use. It's called SDR Sharp. It can average the signal over time that minimize the noise minimize the temporary noise. So we do this to measure the environmental noise, and I conducted the measurement in A, B, C, D 4 places. We do this measurement in different places to find the least noise place to place our bigger telescope. Just get familiar with the system. So we will discuss the data later, and here comes to the bigger telescope. This is 3 diameter, and it's called PRISM Small Radio Telescope. Here's the LNA as the amplifier, a filter, SDR, similar, and time average algorithm. So as you might expect here, you might see here, there's a little change of the feed. So that is because we adopted MIT Small Radio Telescope feed, which is a feed designed by MIT, and it focuses at 1.42 gigahertz. This is the frequency that when hydrogen drops from its first excited state to its ground state, it will emit this electromagnetic wave, and this is happening inside every star. So when we observe this frequency of radio waves, we can see all the stars in the universe. Here it is made of aluminum pan and spiral copper stripe. Yeah. After we constructed the feed, we made a test to the performance. It is called one-port measurement, also known as S11 test. It measures the signal that is being reflected back to the antenna. So here at our aiming frequency, we can see that it has a less than negative 10 decibels reflection, meaning that over 90% of the signal is successfully transmitted by the feed into the LNA, meaning the feed is quite it's functioning well. So then it comes to website control. Initially, we thought about sharing the telescope globally, because we think that thousands of dollars telescope shouldn't just benefit one school. It should be benefiting more students around the world, providing them the opportunity as well. So after I discussed with this wise guy, Mr. Kemp, my engineering teacher, we found a telescope called Picture Telescope online. It is website controlled, so we want to get a similar system. This is the flow graph of the system. First, you go onto the website, you send a request, and the Firebase, which is an online database, will update it, and it will trigger the local Python program to run an observation and later send the data back through email. This system has two advantages. First, it's very easy to access. Second, because the Firebase database, it can protect our school locally, so we won't suffer from cyber attack. Okay, so this is the website design. As you might expect, observation name, and then several parameters that is necessary for observation. In the end, email address, which we use to send back the signal, the data. So we conducted a test. So this is my random type observation name, and we successfully received the data through email. The website was once posted, but due to the overheating of the local computer at the summertime, we stopped running it. So this is how we track celestial objects. You can see the big dish here. This is a model made by SolidWorks. We adopted a 3 RPS parallel manipulator, which means that the 3 bottom joints here or here, they are revolute joints, meaning they have 1 rotational degree of freedom, and the linear actuators, like the iron rod here, they have 1 translational degree of freedom. And the AB3 points, they are the top joints. They have 2 rotational degree of freedom, meaning they're either ball joints or universal joints. So this is the sketch model of it, maybe. So the 3 linear actuators are half extended, 1.72 meters long, as here. And this is the bottom plane, top plane. Each linear actuator is leaning 15 degree angle from vertical to the center of this bottom triangle. And this allows the top surface to have a maximum inclination of 70 degree at any angle. So you can go 70 degree like this. And here, here is a video that shows how the telescope tracks the sun at Princeton on July 19th. Okay, if you want to see the video, just find me after this video. All right, so here are the data results. First is the RFI measurement. The horizontal axis is frequency in megahertz. The vertical one is relative intensity in decibels. The red ends are the noise peaks that we label using statistical methods. So this is site A in front of the main building. Maybe you remember, maybe not. This is site B. this is side C, this is side D. So over the 4 graphs, I think we didn't observe there's a really high change, really large change in the signal structure, neither the intensity level. So we put this into a minor factor. So we think about the availability of sky and the availability of power source for our telescope as the first 2 factors. Therefore, we decide to put the telescope here at point E, which is in the back of our dorm. It has a very large grassland, low skyline, and power source. Yeah. So, and then we look into a set of data that NASA posted. They are the different frequency noise sources. So at 1,000 megahertz here is the Wi-Fi signal, and then here is the aircraft navigation, GPS L2 and GLONASS L2 signals, and here PCS cell phone base station. Then it comes to the bigger telescope. So this is the scan of the bigger telescope. You can see several peaks that are the same here, 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 and here, right? But we see 3 new chunks of data, and they are not in the NASA post. So I look into American frequency allocation, something about the radio professional usage, and I learned this one is radio navigation satellites. So basically the similar satellite of GPS in different bands. And this one is telemetry, so the communication between plane and ground stations. And this one, the first several are weather monitor satellites, and the ones here are cell phone communication and other mobile communication. But most significant in this graph is the peak here. This one is right on the 1420 megahertz place, which is the aim frequency that we want to see of hydrogen line. And we inferred that this is the hydrogen line signal, but we still need more observation to confirm that signal. So in short, we have conducted a lot of steps, including RFI measurement, the first light of the big telescope. We have developed a remote control system and 3 RPS parallel manipulator. So in the future, we will use an artificial signal source to calibrate the telescope to make it more accurate, and we will construct the base. It is finished design and is in manufacturing. And we will polish the website. We will also incorporate the remote control of the parallel manipulator into it. And in the end, we want to use some RFI mitigation methods, maybe active noise cancellation with a reference microphone, just like the AirPods Pro, how you make it silent surrounding. And also we want to use CNN neural network to help identify the noise blocks. So thank you all for listening. I want to thank those people, my teacher, my peers, my school for support, and my parents for supporting me throughout the project. Here are my contact information. If you want to learn about telescope, you want to try it, you can take a photo and later contact me. And those are the citations. Thank you so much.